So for the second method, so to solve the turbulent boundary layer, so we call it as the empirical form. So the empirical form is in general terms, we try to calculate layer by layer. Every molecule inside that boundary layer is need to be calculated, and then we plot a graph, and from the graph, so we take the value what we want. So this is the idea. Okay, so I try to make it simple because so it is not easy to solve this by using the calculation in final exam actually. So I hope you could read this one. So in many textbook they were written about this empirical method. So the idea is the researcher found that it has two region when we plotting the velocity. Okay, you need to imagine that in empirical method you will have a table like a Blasius. So means so let's say this is our uh, plate here. So this is our boundary layer. So means that we have a y-axis here. So means that we could plot all the velocity inside this boundary layer. Because you know, like a simulation, you have so many coordinates. So you will have all the equation. All the you have equation, you substitute the value of coordinate x and y, and finally you will get the value. Okay, that is the idea of numerical. So when we plot all the graphs, so it is found that we will have you will have two regions, which is the inner region and the outer region. Okay, I think these notes I already upload in my website, so later on you will get it. Okay, so you will see it. So the idea is when researcher plot the graph, so they will find that it's the trend is will become like this one. So it will comes a little bit, so it increase a little bit, and suddenly, so it will start to steady at this point. So because the numerical will take care all the phenomena, so they divide into the inner region here. So and then they start the outer region here. Okay, but normally people will go for the outer region because the inner region here it's happen very fast. So they will it is okay for to ignore about that, but in these notes I just want to show all the calculation later on. Okay, so we just go for the just the important equation. So for example, we need to calculate the u over u tau here. So mean the u is the velocity, the velocity that influenced by the free stream velocity here, and u tau here is the velocity that influenced by the shear stress. Okay, so and then we the u tau here. Okay, u tau here is tau naught, mean shear stress at the wall here, divide by the density square root. So we could get the shear velocity. Okay, this is the definition of u tau. So and then the velocity for outer region is u minus u over u tau. So which is it is can show as the function of y over delta. So it is why this happened because the velocity here have defect. So it's okay. Just here until the end of the slide. It's, okay. So and then I shortcut everything. Okay. So it is assumed that for the local friction coefficient, so the local here, so it is equal to CF, it is equal to CD here. So from the graph, we could find that it is the curve fitting. So from the scattered data from the experiment and so on, so we could conclude that the local skin friction coefficient can be assumed it is equal to this one, 0.455 over ln square, ln of 0.06 Reynolds number x square. So this is the value of CF, and the most important is the value of CD. So the value of CD here is equal to 0.523 over ln 0.06 Reynolds number X square. So it is okay for the empirical. So for this syllabus, it is okay for you just to remember this equation for this one and also for this one. Okay, because this is the representative value. Okay. So, and then finally, okay, also this equation you need to remember. So, fortunately, you are open book test after this. Okay. So, this equation also you need to remember because this equation is the equation to calculate the value of delta. So, means that by having the value of u tau here and also the value of u tau here, so this is the kinematic viscosity. Okay, by having these two parameter, so u infinity here is the free stream velocity. So means that the free stream velocity, if the wind or the water flow 5 meters per second, so substitute the capital U with that velocity. Okay, so if you have all these parameter, means that you could calculate the value of delta. Okay, let's say we have example here. So in example 1 here, so estimate the boundary layer thickness at the end of 4.5 meter long flat plate if wind flow on it at 30 meter per second. Also calculate the drag force on the one side if the plate is 3 meter wide. Use empirical data. Assume that the temperature is 20 degrees Celsius. So the 20 degrees Celsius is just to make sure that we take the correct value here. So let's say the boundary layer thickness can be calculated by using this equation. So however, we need to calculate what is the U shear stress here, U tau. So U tau is equal to tau naught over rho, and tau naught can be calculated by using CD times 1 over 2 rho U square here. And the value of CD here can be calculated by using this equation. So first, we need to calculate the value of Reynolds number. So Reynolds number is rho u x over mu. So it also can be written as u x over nu. So please make sure that you could differentiate between velocity and kinematic viscosity. So we substitute everything. So we get it is around 1.9 times 10 by the power of 6. So and then we use this Reynolds number. We substitute into this term first. So it is equal to 13.1926. So then we could calculate the tau naught here by using this equation. Okay, so it is equal to 1.416 Pascal. So from here we could calculate the u tau here. So and then it is equal to 1.084 meter per second. So and then we could substitute all the value into this equation. So and then we could determine the value of delta here, which is equal to 0.05567. So this is the common value, the common ideas in the empirical method. So the drag force can be calculated by using this equation. So this is the calculation of the the CD. So we substitute the value of Reynolds number here. So we get it is equal to 0.003. Then we use this common equation, CD 1 over 2 rho AU square. So we substitute the area of the plate here. So 4.5 times 3, the width is 3. So we get it is around 21.94 newtons. Okay, so here, because the question asks to calculate the drag force only for one side, so it is okay for us to have our final calculation is 21.94. So if the question asks to calculate the total drag force, what you need to do is you need to imagine that we have a plate here. So and then the boundary layer is actually occur at the top and at the bottom. So you need to multiply times 2 here to get the total drag force. Okay, so I simplified that one. Don't worry. Okay, so and then for example 2. Okay, so estimate the maximum boundary layer thickness and the drag due to friction on the side of a ship that measures 40 meter long with a submerged depth of 8 meter, assuming the side of the ship is approximated as a flat plate. Okay, the ship travel at 10 meter per second. Use the empirical methods and compare with the result using the power law model. Okay, this will give us a big difference in calculation. I mean, in final exam, in final answer. So you could get the value of okay, the value of temperature here. Maybe I take 20 degrees Celsius, so we use 998 here. Okay, I'm not sure that what. Okay. Okay, so we take properties of 5 degrees Celsius, for example. So it is equal to 10 kilogram per meter cube. So we could calculate the tau note here. So by using this equation, so I hope you could understand this. Previously, I show you how to calculate this one. So we could get it is around 82.8 Pascal. And then from here, we could calculate the U tau here. So we get 0.288 meter per second. So we calculate by using this equation, so we could get the delta is equal 0.384 meter. So and then, so we calculate the total drag force. So this is the equation to calculate the CD. So and then we could get it is equal to 0.001904. So we use this equation to calculate the total drag force. So we get it is around 30,464 newtons. So this is from the empirical methods. So let's say we calculate this one by using the power law. Okay. So and then we check the Reynolds number. So the Reynolds number is here. Okay, because it is 40 meters long here, the velocity is 10, and this is the kinematic viscosity for water at 5 degrees Celsius. So it is around 2.6 times 10 by the power of 8. So we assume that the here the U over U is Y over delta by the power of 1 over 9. So here, please make sure that you understand that 10 by the power of 8 here is actually 1 times 10 by the power of 8 until 1 times 10 by the power of 9. So mean 2.6 is here. So means we take the value of n equal to 9.
So, doctor, in this case, we should see these calculation or these ratios. Our velocity profile will depend on this ratio.
Yes.
For the turbulent.
Yes, for the turbulent.
Okay.
Okay, you need to choose. But normally, if you don't have 1 over 7.
Yes.
Okay.
Thank you.
Okay, so for the textbook, from the textbook, let's say, as I said, we cannot use the idea of viscosity, shear stress from Newton law of viscosity. So we need to use the shear stress from the Blasius. So and then from the textbook, we could get that it is equal of this one. Okay, 0.023. So and then we equalize with the von Karman equation. So I simplify this thing because you could do this calculation. So the rho u square d theta dx equalize with this one. So you will get it is 9 over 110. So and then we equating these two equation, mean the shear stress from the von Karman and also shear stress from the Blasius here. And then we get delta is 0.433x. We substitute the value of Reynolds number, so we get it is 0.358 meters. So if we compare this one, so therefore the empirical methods, we found that the boundary layer is a little bit thicker compared to what we get from the power law method here. Okay. However, the boundary layer is actually not so thick. Okay, that's why the difference is not so obvious. So it is about 6.77%. So normally in terms of boundary layer, so it is okay for you to use both methods because the error is not so big. Okay, because if you are focusing on to get the value of boundary layer thickness. Okay, however, if we calculate the value of drag force here, so we calculate the value of CD, so we get it is around 0.071 from the power of 1/9 there. So we substitute in the equation, so finally we could get it is around 23,500 newtons. So if we compare from the empirical and power law method, we found that the empirical method give us 30,000 and the power law only give 23,000. So the difference is about 22%. So means that if you are solving some things, okay, please make sure that, as I said, the empirical is a little bit complicated, but the result is accurate because if you predict the drag force is just only 23 newtons, so mean you will maybe you will have some blinch or something, some hiccup after this because your estimation is not enough for that situation. So, but however, in this question, I simplified everything, but because I tried to show the difference between the empirical and power law. But in reality, actually, so you need to calculate the empirical by using the numerical way. Okay.